Welcome to our first tutorial. It's my privilege to... Can you hear me okay?
Yeah.
Okay. It's my privilege to introduce our first speaker this afternoon. Russell Church is someone that has been with SQAB for many years, is known by most of you. He's a good friend of our society, and for the few of you that may not know him, a few highlights from his career, and then a few highlights from his personality. Okay, Russ obtained his degree at the University of Michigan, his bachelor's degree, and then his master's and PhD dissertation at Harvard. And then he moved to Brown University, where he has been since then. He tells us that he has a long-term love affair with computers. In '64, he fell in love with Don Blau's classic Lane computer and worked very hard to get the PDP-12 computer in 1971. It used the computer mostly to control experiments and recording results. Later, he began to use the computer for simulation. That's the topic of his talk today. He was president of Eastern Psychological Association, president of Division 3 and 6, Experimental and Physiological, of the American Psychological Association, and most relevant to this tutorial, in '81, he was elected president of the Society for Computers in Psychology. More recently, Russ has been involved in trying to get people to archive their data, basic research, and make it somehow available to everyone in the scientific community. So he has been a co-chair of the National Institute of Mental Health workshop on data archiving for animal cognition research. As a chair of the publication committee of the Psychonomic Society, he helped to develop policies of more open access to published research of primary data. He is a very prolific researcher, very wonderful experimentalist in many areas in the psychology of learning. He's also in the board of editors of several journals, including the Journal of Experimental Analysis of Behavior, consulting editor of Learning and Behavior, and an associate editor of the Journal of Reviews, American Cognition Society. Okay, so much for his career, brief highlights. Now, let me tell you a few stories that his students told me, at least. So, one thing that I found interesting, I asked my former student, and then Russ's student, Richard Keith, tell me something about Russ's personality that we don't know. And he mentioned that Russ is very hardworking, goes to the lab almost every day, and then stays from 9 to 11:55. And then at 11:55 he goes home to have lunch. Even if you're in the verge of solving the mysteries of the universe, as Rich said, he goes home and comes back at 1. So perhaps there is a moral here, like the solution to the mysteries of the universe are at home with a family lunch. Okay. As you know, Russ is a big chess fan. And so at one time, the story goes that the programmers of Deep Blue wanted to train the machine with someone just before they moved on to play the machine to play Kasparov, the world champion at the time. So they invited Russ for a match, and he was a psychologist, and he put some psychology into work, and so some kind of psychological warfare started when, as someone put it, he wore a baseball cap and he turned it backwards. So during the match, so that disrupted the machine, and we wound up with a draw. As you know, the machine went on to draw with Kasparov and then to beat the next time. So one of the major points that these students refer is Russ's wonderful sense of humor. I'm sure we will have a few highlights of that during his talk. So he's going to tell us about simulations of quantitative models of behavior, and I'd like to ask you to join me in welcoming Russ.
Thank you very much, Armando, for such a gracious introduction. I wish I had time to tell about the telephone call I got from Bobby Fischer, but I better get on with it. The general problem is how to simulate quantitative models of behavior. And what I propose to do is organize this talk by a 7-step recipe. First, I'll describe a general problem, which I'll refer to as Skinner's problem, which is trying to understand the determinants of behavior. Then a specific problem, just a simplest schedule of reinforcement for one rat. We'll conduct an experiment, specify a model, and then estimate the parameters, evaluate the validity of our bit, and then evaluate the generality. With respect to the general problem, how well can we predict behavior? One standard idea is not very well because behavior is controlled by the brain, and the brain is very complex. Or it's determined by the environment, and the environment is very complex. Or there are all sorts of things we don't even know about, and we call them random factors, and there are a lot of them. Or maybe it's because psychology isn't good enough. It's a young field, 150 years old, maybe. Or maybe it's us, that we're not up to the job. We're just not smart enough. That's one standard view. You can't really do it because it's a very complex problem. Another is, can't do it very well because all behavior is not determined. Maybe most behavior is, but some isn't. Or maybe it's like some opponents of evolution say, well, determinism is just a theory, an idea. Or maybe it's part of the game of science. We pretend that it's determined, but we know that it isn't. Or maybe it is determined a lot by the biology, a lot by the environment, but we have to worry about a little bit of free will. Now, I had some lessons from my mother that you are responsible for what you do, and you may become what you want, and if you get sick, it's your fault. Now, my views are that, and here you'll see I give references to my limited philosophical sources, but I believe that behavior is determined by biology and experience, and I believe that free will is evolution. But number 3 is the important one. It's that the predictability of behavior does not depend upon one's beliefs about either determinism or free will. Just because a person has free will, it doesn't mean you can't figure out what a person's going to be doing. And just because behavior is probabilistic rather than deterministic doesn't mean that you can't predict in some sense what they would do. And so I come to the view that we can predict the behavior of a rat, at least in a simple environment. But this depends upon what we mean by predict. And I don't mean predicting from intuition or from linguistic skills that we may have to confound one with arguments. But I mean a formal model that is quantitative, not just qualitative, because that's too easy. But not absolute prediction because that's too hard. An absolute prediction would be that I could try to predict what the rat would do in every given second. And that would be very difficult. And if it could do it, then the question is, how about the millisecond? Perhaps it does, sometimes harder. So the goal is not absolute prediction, but rather relative. Relative to what? And the suggestion I have is that our goal should be to try to predict what the rat will do from the model in a way that is equal to the prediction that can be done from other samples of that rat's behavior in the same situation. Something that I'll refer to as the Turing test. Well, so much for philosophy. Let's move on to part 2, which is a specific problem. We have a rat in a box. This is just an active rat waiting for instructions to begin. And we will say, well, here you are just in this box, do something for us. And whoops, it doesn't do it. Oops, sorry about that. I put my mouse in the wrong place. And we will try it again. And there it goes. So we see what the animal is doing here is exploring the bedding, the floor, a little bit of exploration, and it's bouting. He's doing this for a period of time. And then it goes over to a drinking tube and starts drinking for a period of time. We have well-defined types of behavior that occur in a bouting fashion over a period of time. When the rat is done drinking, it will go do something else. It went over to where the food cup is. There's no food there, but just checking it out and looking about. And then another little drink, but now mostly grooming. Facial cleaning here. Continuing on the face, moving on down to the lower body in just a moment. Okay, fine, you can stop. Very good. So, this is the kind of behavior we have, but without a procedure. We just have the rat in the box here. Let's go on to a procedure. An experiment consists of the rat in the box, but a procedure that is sending possibly stimuli, although our procedure today will be so simple there are no stimuli, and possibly food reinforcement. The rat, on the other hand, sends back a response, and the procedure records it. So what we have is a rat we looked at making some responses, a procedure that will, under some conditions, send food in, and that gets recorded. More specifically, let's take the case of a procedure of a 2-minute fixed interval schedule of reinforcement, in which the notation there is a cycle is defined by the 2 slashes after 120 seconds. That arrow indicates a head entry response, results in that solid triangle which represents food dropped. And what gets recorded is the time of each response and the time the food is delivered. Over on the right column, you see the observed data, the various times to a 2 millisecond resolution, where 19 represents the code for food and 8 represents the code for breaking a photo beam at the head entry of the food cup. And those little asterisks I just added later so that you could see that in this particular cycle, there were arguably 3 bouts of head entries. There was one at around 7 seconds, there was one at around 70 seconds, and there was one at around 117, close to 120 seconds. And that would be what it is we have to work from. Now, you can see if we had many of these cycles, as we do, this rat was trained for 50 sessions, 2-hour sessions, 60 cycles. It would be possible to take these data and make them into a mean response gradient where the dependent variable would be responses per minute and the independent variable would be time since the last food. And we get a familiar gradual increasing function of data from a single rat. Very familiar curve, and one that we will get back to after we have a simulation to work with. So now let's change our focus and go from data to a theory. And you will see this looks like something we've just seen before. The only thing is it had rat in there before, and now it has model. And that makes it indeed the ideal. That is to say, a model is something that has as its output responses and its input stimuli, if they were there, and reinforcements and procedure report. So the way we will treat the model is exactly the way we treat the rat with respect to input and output. Now, I'm going to describe, just so that we have something concrete to work with, a particular model, one called packet theory. And here I would say you can decide for the next few minutes to adopt one of 2 attitudes. One is I will try to explain this carefully and completely, and this will be of interest to some of you. And others need not worry if everything doesn't come through right here, because all you really have to know is, oh, so the model is going to say what the responses should occur. And we're going to compare those, and you can come back aboard in the next little section where we take the data and we take the output of the model and start doing comparisons. And in some way, this is very specific to this kind of problem, but if we just take it as we have data from one source and simulate the data from another and comparing it, the details of this particular theory is not essential. What we have in the upper left-hand corner is subjective time S as a function of time. Let us just assume that it's S equals T. This would be for a single cycle. Now, there would be memory that will be of the expected time to the next reinforcement. That is a linear combination of what was perceived and what is remembered. And then there will be a decision based upon whether that memory is above or below a threshold level. The threshold will have 2 parameters, mean and standard deviation, assumed to be normal. In this little movie, we have a single cycle in real time. 6 seconds has passed so far. We can watch the clock. We only have to wait until 120 and it will be done. What we see is perception just gradually increasing as a function of time. Subjective time increases. The value in memory is still well above that threshold value. At some point, it will drop below. The value of the decision, that R, is either at one level, the upward level, or at another level, a high rate level. And this is the rate of initiation of a pact. And so, in this particular cycle, the time at which this occurred is at 80 seconds, and so from 80 seconds on, it will be at the high level. A very, very simple notion that will then lead to something that produces an output. So far we have no output. These are internal variables that are not directly observable. When it reaches this, the perception then can be created, that can be used for the next cycle that will be combined in the next updated. If a packet is emitted, and this will be a probabilistic event, it will consist of some number of responses, here assumed to be a Poisson distribution with a mean of 5 responses. The subjective time is increasing. If this probabilistic one occurred even in the upper level, there was a packet of a couple of responses. This will just keep going for 2 minutes. I won't make you wait for 2 minutes. But after it passes 80 seconds, the rate increases and we'll be getting additional packets. Well, to instantiate this in a program, the essential parts are the following. Initialize the model, initialize the procedure, which here would be the food interval 2 minutes. Initialize the model, which would be setting the parameter values, such as the value of R, that rate, and the mean and standard deviation of the threshold value. And then for each clock pulse, which will come set typically for 1 second from beginning to the end of the session, we will determine if there is something to do in the procedure, determine if there's something to do in the model, and go around until the end of the session. That's the end. The procedure must decide in this second shell who be delivered or not. The model must be decided. Should I update memory, something that happens when a reinforcer occurs? Shall I update the state when pass through the threshold value? Shall I initiate a packet, probabilistic event, and when to respond, which has to do with the number of cycles of the random sample from the wall distribution. When this is ended, we can evaluate the validity with cross-validation and then record the time event codes, in this case food and response. Now, what you can see is that there is great similarity in what is obtained for the observed and the simulated data. In both cases, we need the procedure. In one case, we need a rat, the other, we need a model. And for simulated data, there has to be some calibration data for setting parameters. The observed data and the simulated data are identical in terms of the number of sessions, the number of cycles per session, therefore the number of cycles. The parameters are estimated on the calibration series, the odd sessions at asymptote, and the model fit is based on validation sessions, the even sessions from the same asymptotic values. And the results, and this is no surprise to anyone with a timing theory, all timing theories for something as simple as this will be able to produce a good fit for a response rate gradient as a function of time since the last food. And this does 2.995, which is a nice number. For some multiple runs, it would be slightly different, but this represented the median of a bunch of runs for one round under this one procedure. Now, we're going to have to generalize this soon, but it's better to deal with one round, one procedure for how we go beyond parameter estimation to, for example, evaluating the validity of cross-validation. Here, for the goodness of fit, what you've seen is that 995, 995.2, between the simulation based on the calibration sample and the data also based on the calibration sample. Now, people are often worried that, oh, maybe there are too many parameters and it's overfitting and so on, and certainly cases can be described in which that's very much a problem. Here, there are rather few parameters relative to the data points fit, so I think it isn't so serious, but it should be checked out. And we can compare the simulation to the validation sample, the cross-validation, and find it's a little lower, but not much, 988. And more importantly, it's the same order of magnitude as the calibration data with the validation data. That is to say, whatever misfit there is seems to be something that is in the random stuff rather than in a bad model. So this says for just dealing with these data, that is the gradients, a model is about as good as it can be, or there may be many alternative models that are equally good, but fiddling with the model to deal with these data would not seem to be a productive exercise. Well, the next problem is to try to evaluate the generality of the model. So it fits those gradients, but what else can it do? The parameters we're obtaining to deal with those gradients. Does it do other things? And what we would like to do is get great generality, which is we have a procedure that is feeding stimuli and reinforcers, in this case just reinforcers, to a rat and to a model. The model and the rat is feeding responses to the procedure, and we're getting two records of time event codes. One, what the rat did, the obtained data, and the other, what the model did, the simulated data. We shouldn't be restricted to just dealing with response gradients. We should be able to take any dependent variable that we want and see if that would fit also. And so, give an illustration from one cycle of a rat. In the upper left-hand corner, we have between one food and the next, the times that responses were occurred by these little lines. Going down, we can translate these responses to a local rate, that is to say, a reciprocal of the IRT, the scale for responses per minute, and then shown at the third on the left panel as a logarithm of that rate. Now we have a comparison of the sample with the rat in the upper right corner. And they're pretty close. We can measure the sum of the absolute differences between them to see how close. And then we can do the same thing for the sample with the model. And in this particular case, the sample seems closer to the rat than to the model, and is. And that leads to the conclusion that this sample came from the rat. It happened to be wrong. And the goal, of course, is to have the model so good that you can only do it by guessing. It'll be 50%. Half the time you get it, half the time you do it. Well, in this case for this rat, the best we could do would be 50%. If we had a really bad model, we would be able to tell all the time 100%. We got it to 56%. Now, what's our goal? Well, our goal is to get as close as possible to 50%, and is 56 significantly different from 50? Oh yes, quite a bit. Probability 0.03. So we had 167 thinking it's the model, and 133 thinking it's the rat, and with 300 flips of a coin, this is different. We've got work to do. We've got to drive it down to 50 from 56% to much less, but it's getting very, it seems plausible that prediction can occur. Now, there is always the question of how general this would be. And for this, I refer to the poster that Lisa McGinnis and I had at SQAB. Yesterday, a few more copies would be available if anybody wants to look at this carefully. I'll just run over it quickly, which is to say, it contained much more than one rat and much more than one procedure. The procedure described was the upper left-hand corner, no stimulus, just food to food, and one of the rats, 42. There are seven total conditions, and what we have here is the data form, which you will see differs across conditions. Conditions differing with respect procedurally to whether there was a stimulus or not, and whether the stimulus was a brief presentation call an event, or a steady stimulus we call a state. It varied in terms of probability, and there are a whole bunch of interesting forms. And what is difficult to see at this distance is that there are both data points and a thin line, and the thin line is going rather close to the data points with fits of order of magnitude 98, 99% of the variance accounted for. So the notion is that the model is probably good across a number of procedures. Now, all you have in that previous one was group data. What about the individuals? And here are the same set of 7 procedures, but showing the individuals rather than the groups. And one sees that there are differences among the individuals, reliable individual differences, but they tend to be similar in shape and clearly different from each other, and not badly characterized by the mean change that we were just looking at, which suggests that there is generality across rats. And to see the generality across procedures with a Turing test, that is, for other dependent measures, we have the one that the one rat was in, the red bar on the left side, and the other 6 procedures, and they're all about the same in the getting close to the ideal 50%. The average was 58%. Again, perhaps a small difference of 50%, but highly significant. So there is still a little work to do. So in summary, I would say that what we need is a good general problem, and I think Skinner's problem is a good way to phrase it. Given a rat in a box with a procedure, what does the rat do? Of course, any given simulation requires a specific procedure. Here we have a rat with observed results, a quantitative model with simulated results, so we have the observed and simulated to compare. And it appears that if one has parameter estimates, it is possible to predict the behavior of the rat with a simple procedure quite well. But the goal of prediction is understanding, or at least the scientific goal of prediction should be understanding. And I think some progress is made toward that by having a validity criterion, namely cross-validation, and having a generality criterion, which could be this Turing test, and finally having a procedural generality criterion that here is just a bunch of procedures that are described, others have been described last year in the SQAB meeting by Georgi and colleagues. But it would be better to have a more principled way for selecting procedures, and that I think that some kind of well-defined universe from which one samples is a goal that we work on. Well, I'd like to acknowledge Mika McGinnis, Paolo Georgi for the style and substance of this tutorial, as well as other contributions and other contributors listed there: Kim Kirkpatrick, John Crystal, Richard Keene, Linda Yee, Marcelo Cano, and Thanks very much.
Questions?
Russell, I wonder if all the complexity in the packet theory is required. I mean, you could actually get away with something quite a bit simpler. A couple of, maybe a little Markov thing, a couple of probabilities, starting, stopping, about that kind of thing.
It would be difficult to establish that there does not exist a simpler theory. What can be easily tested, that we probably have not done in a systematic way, is to break any one of the parts that were described and see if that breaks the predictions. So, for example, if we break the boundiness, would it fail? And the answer is certainly it would fail. I didn't show this, but we have, let's say, IRT distributions. And for the IRT distributions, if you don't have boundiness, you obviously don't have whatever it be. But whether there is some simpler Markov chain, that, of course, has to also deal with the generality question, which is to be able to handle, without change, many other procedures and many other dependent variables. It's a challenge. I think that's, this is only a target to be, for other groups to be proposed.
I have a question.
Yeah.
I feel there is some tension when we build these models because we try to reach two goals that may be unreachable at the same time. So if you try to reach one, you will not reach the other, or vice versa. And those are the following. On one hand, I see a very simple procedure, like you give them food every 2 minutes.
Yes.
And the rat displays a behavior that is highly structured in time and perhaps even in space.
Yes.
And you try to capture the fine structure, like the bound structure, the intervals.
Yeah.
And so I would summarize this by saying you're going for depth. The model has to predict in depth the behavior of the beast. But then you have another goal with these Turing tests, that is generality.
Yes.
Across procedures,
Yes.
and variables.
Yes.
And I wonder what your thoughts are on the fact that depth and generality are a zero-sum game. If you win one, you lose the other. Can we reach both at the same time? Are we not trying too much?
I think it's good to aim high and see if it's possible. And I would say that the definition of predictability would be that we would want to achieve both and not sacrifice one or the other. But of course, it's a question as to whether that's But I agree with you. When you're working for depth, you tend to add more and more things. But then if you're working for generality, you would not want to have things that are not needed for something else, so that there is a danger of getting overly complex. My feeling is this, at the present time, is not too complex. And the question might be, well, what do I know would not be fit as we have it now? And there are some things that are actually very simple to track, which would be like a peak procedure. And why is that? Well, it's because we need maybe one more thing, but if we put the right thing in, it may handle many things rather than just a given procedure. So I would always, when trying to get greater depth, try to make it such that the thing is very general. I think owliness is very general, and temporal discrimination is very general. So that I'd like not to have to put in things specifically for some particular procedure.
Any questions? Can I yell?
You can yell at me, but I may have to repeat your question. Because I can see it. Yeah.
I thought your answer to Armando was good, because obviously the rat manages these things, but that mentioned around where the rat manages.
Yeah.
We're trying to model the rat at some level, and we should retain both. One thing that seems really obviously missing, which is something you might consider as like motivation elements in terms of the number of rewards, the amount of rewards that you could. The other one, this is of course an idea. Rats do other things in the box other than show this behavior. So are you interested in doing some?
Sure. The first one I take to be a hostile question. The second I take to be a friendly question. The hostile question is, you don't have anything about motivation here. Motivation is involved in the soul. Yes, that's true. Motivation is not here. So in defining the range of things, I don't have anything about whether the animal just had a very big meal before it goes in, things of this sort, or even in a long session, satiation. So this is not involving motivation at the present time, and I don't have good insights as to how that can best be incorporated. But at some point, if it did everything else, then obviously others, I would take it and say, now, what can we do about this giant problem of motivation? So yes, that's a weakness. The other one, I know, we wish to be a strength, and we don't have yet, which is when you saw that little film clip of the rat doing some exploration, some grooming, some drinking, some head entry, and I had levers in there requesting that. We're not doing all the behavior. We're just doing a single one, which is the head entry response. We're not even doing the length of time the head is in there before it gets withdrawn and so on. So it's just a single point event is all we talked about today. But I'm delighted, if you don't mind my saying this publicly, of your interest in working with Nico McGinnis and others of us on matters having to do with trying to get an automatic way of recording all of these other interesting behaviors, including exploration, various types of exploration, grooming and various types of grooming, as well as the easier ones like the drinking and bar pressing and head entries. And with the help of bright people and good programs like MATLAB, and great interest by people who know what animals really do, we hope that that will be successful.
Hi, Dr. Church. I was wondering if you could talk a little bit maybe about why you chose to use Turing tests as opposed to doing direct comparison of the things that were likely controlling the judge's decisions in terms of the aspects of data.
Yeah, the Turing test in contrast to, could you amplify just a little bit what the alternative would be?
Well, maybe for example, when you're comparing two models or mathematical models, you would compare the R-squareds and fits. So so maybe some things
Yes.
analogous.
Yeah.
Is that clear?
Oh, yes, it is. So the question would be, I think the key problem with our emphasis on summary measures and comparing, let's say, a summary measure from the data with a summary measure from the simulation is that we have to have some principled way of choosing the summary measure. And I think very often the reason we choose a summary measure is because other people did it, or that's a definition of memory or something else. But it seems somewhat arbitrary. Whereas one of the nice things about a Turing test is that you look for any discrepancies that you can find. Now, and Turing did it. He proposed it in 1950. He said in 50 years, which is now past, if we had computers with particular power, which we have now, and we took an average interrogator and gave him 5 minutes and tried to achieve a particular goal. But the weakness of that proposal was that it was kind of subjective. Who's an average interrogator? Well, they're asking the question and of obtaining the answer. And so this is an attempt to deal with the weaknesses of selection of the procedure, the questions, and weakness of the evaluation of the answer, which is having it dependent upon the strength and weakness of the analyst. But it is striving for generality that might not be obtained by one dependent measure at a